Okay, welcome back everyone. So we're going to wait another 2-3 minutes for everyone to join. So unfortunate thing is that the campus wire service is down. It always happens like that, right? In the crucial moments, things are going to just go down. So we're going to largely use emails to send out any announcement until the campus wire service is back up online. Until then, if you have any questions, please do leave the questions on the Zoom group chat here for this lecture. Meanwhile, let's hope that we hear back from Campus Wire soon about this service outage they have there. This is not good. But again, everything is being recorded, so you'll be able to watch any of these videos later. So the first lecture was also recorded earlier. Don't worry about it. Yeah. This is a bit unfortunate, but let's give it some time, yes. We have the 42 participants, so let's wait until we get like 45 or even 50 participants before we start the actual lecture. All right, 47. Let's wait for 3 more. I hope you all enjoyed the Q&A with Yashua Bengio. I was also online. I thought his answers were really nice. And then the very good questions you asked. And then as Yashua mentioned, at the end of the day, it's not about, whether you get a big money position in Silicon Valley or not, but it's more likely where you stay, where your heart belongs or where you want to be, and then trying to build a local community around it. And then maybe from there on grow into the global, let's say, corporation or the organizations. Yeah, so don't worry about where you are or what you're trying to achieve, but trying to enjoy the whole thing and then see what you can make out of this. All right, so we have hit 50 participants, so we're going to continue from what we took off earlier. So earlier today, we learned about what it means to build a recurrent neural network, and then what are some of the difficulties involved in building and training these recurrent neural networks. Mainly, we focused on the vanishing gradient issue. And then we talked about how this vanishing gradient issue and exploding gradient as well manifest themselves not only in recurrent neural networks, but also with the feed-forward neural networks. What that means is that all the things that I talked about are not only confined to recurrent neural networks, but also applies to any of the recently proposed architectures such as the transformers, residual networks, or anything that you can imagine. So in other words, you want to always clip the norm of the gradient regardless of what kind of network you're training. You also want to ensure that there will be some kind of shortcut connections, or often called residual connections, in your network, so that there is a shortcut created across all possible time differences or the layer differences, and that facilitates propagation of the error signal all the way from the very end of this directed acyclic graph to the beginning of the directed acyclic graph. And then our experience tells us that that is really the way to go in order to train a very deep and very powerful neural network. So now we have 45 minutes this lecture, and then here I wanted to spend some time on trying to go deeper into how to derive this attention mechanism that we talked about when we talked about how we can build a machine translation system or neural machine translation system. One of the key point there in introducing attention mechanism was to give a model ability or the capability to figure out what is the relevant subset of the input that it needs to focus on at every time step. What it means is that at every time step t, so based on what has been translated so far, that is from y1, y2, all the way to yt minus 1, this attention mechanism looked at each and every one of the source representation, that is H1, H2, H3, H4, and H5, and then try to assign the weight to each one of them according to this weighting function, which is yet another neural network. And then this weighting is going to reflect which one of these H1 to H5 is most relevant or most important for predicting the next token, that is YT. So this is a really important concept here, right? So this attention mechanism allows us to build a neural net that is able to work with a variable length or the variable sized input, because for instance, in the case of machine translation, the length of the source sentence differs from one sentence to another, while without having to compress this variable size input into a single vector, because the compression is very, very difficult. So instead, what this attention mechanism allows a neural net to do is for this neural net to focus on a smaller subset of the input every time step in order to avoid the necessity of compression. That kind of makes sense, right? So then where does this idea come from? There are many different reasons or the many different ways in which you can derive or you can arrive at this attention mechanism. But today at this lecture, we're going to think about arriving at this kind of attention mechanism, and more so of the latest version of the attention mechanism that is a fully attention mechanism, or called transformer, starting from the gated recurrent units. Because at the end of the day, other than this intuitive explanation of we want to make a neural net to be able to focus on a small subset or adaptively focus on smaller subset of the input, which is very intuitive, we can have a mathematically more appealing explanation why we want this attention mechanism. And the mathematical appeal has to do with, again, with the vanishing gradient. The fact that we have to compress a long sequence into a single vector, or the fact that it is difficult to do so, has everything to do with this vanishing gradient. Because what the difficulty comes from the fact that it is difficult to capture the influence of small perturbation in the input on this single hidden vector. And then the difficulty of capturing this influence is precisely what vanishing gradient means, right? So let's go back to the gated recurrent unit. LSTM is what we call is a shorthand notation of the long short-term memory unit. So long short-term memory that was proposed by Jürgen Schmidhuber and Sepp Hochreiter in late 90s. And then it does have almost same kind of motivations as the motivations we used to create the gated recurrent unit earlier. So gated recurrent unit is so much more recent, but at the end of the day, it turned out to be essentially the same thing as the long short-term memory units. And then the key idea behind both LSTM and GRU is this additive update. That is, instead of trying to simply replace HT to be the HT tilde, where the HT tilde is the f of the xt and HT minus 1, which is often a simple hyperbolic tangent function applied to the linear combination of the input and the previous hidden state. So instead of doing so, this will be the naive transition, right? What we want to do is that we add this new thing to the previous hidden states. So it's much more additive than replacement. So the naive transition is the replacement. So the update in the naive transition is going to replace the entire hidden state that is ht minus 1 with this ht tilde. There was a naive transition, but LSTM and GRU update the hidden state by addition. So it only adds on top of what is already there. And then this additive update is how we create, how LSTM and GRU create these linear shortcut connections. Because we add the, so for, let's say at time step t, ht plus 2, what we do is that we are going to add the new thing to the ht plus 1, and then ht plus 1 was also some addition between ht and a new value. And effectively, when we look at the ht plus 2, it is the addition of ht plus 1, and some new value. So that's what we mean by it is an additive update. And then this is the most important idea behind the success of the recent deep learning, in the sense that if you remember, you must have learned about the residual network, right? Have you learned about residual network so far, or the ResNet you call it? If you have so, please click yes button on the Zoom. Okay, 1 yes, 2 yes, 4, 5. Okay, all right, going up. Okay, so everyone knows. And then if you remember from the residual network, it's essentially the same idea, except that in residual network, they don't have this adaptive connection. It turned out that this adaptation is important, but not the most important component. The most important component is this idea of addition. So in the residual connection, let's say when you compute the hidden state at layer L, you're going to have a very complicated block of computation. So having a multiple convolutions and pooling that is computed based on the earlier layers computation. And then what you do is you're going to multiply this. You're going to add the earlier layers hidden state with the linear projection. And then this is also additive update, right? And then this is what the residual, oops, I'm sorry. This is what the residual block does. So this F is going to be the nonlinear computation, such as a convolution and so on. And then this latter part is where you add the previous hidden state directly to the output. That is indeed a skip connection, and then that's, or sometimes called residual connection as well. And then you see the stark similarity between the update of GRU and this residual connection. That is, always provide the previous hidden state into the next hidden state using the additive term. Now, in this case, once we have this, we can think about unrolling this gated recurrent unit all the way. So what do I mean by the unrolling it? So HT can be written, so this is a usual GRU update equation. We have the previous state and the newly computed one. But then now we can take this HT minus 1 and then rewrite this HT minus 1 in terms of the GRU update equation again. That shows up here, right? So HT minus 1 is computed as the weighted sum between HT minus 2 and the new value of the hidden state HT minus 1 tilde. And given this, we can again rewrite HT minus 2 into its own update equation, which states that the HT minus 2 is the weighted sum between HT minus 3 and HT minus 2 tilde. And then we can go all the way. And then what we can do is we can rewrite this whole thing in terms of the weighted sum of all the previous hidden state. So it's going to be the weighted, right, sum of all the previous potential hidden state or the candidate state. How did we get that? Let's look here. So we see that for the last one, H tilde T, the coefficients is 1 minus ut. So that's where the 1 minus ut comes in here. And then all the others are going to do the same thing. And then for the h tilde t minus 1, let's look at this one. We have the 1 minus ut minus 1 times ut. So this is almost like a binomial expansion here, right? So every time we're going to look at I, and then from I until the latest one, we get the uj. And then from up until I, we have the 1 minus u1. So we can just rewrite it this whole, let's say, GRU computation over T steps of GRU update. So that we can rewrite the T steps of GRU update as computing the weighted combination of all previous hidden state. So weighted combination summation of the all hidden state. Now what this implies is that another way to look at these gated recurrent units or the LSTM is to simply to compute the weighted sum of everything that was computed before instead of doing the recurrent computation. From here on, so we're going to start from this 0 and then trying to get to the attention mechanism from there on. So let's go back and then let's see, what the question is from iPad is, could you please clarify for me the intuition behind using 1 minus ut? Ah, yes, so this is an interesting question. Maybe it's an important thing to look into. So here, let's look at this 1 minus ut and then ut. So what gated recurrent unit is doing is to compute the convex combination between ht minus 1 and h tilde t. In the case of LSTM, they don't compute the convex combination between the new state and the old cell state, but just a linear combination. And then when we say linear combination, what it means is that these coefficients, let's try to use another color here. These coefficients in front of two terms do not have to sum to 1. But in the case of gated recurrent units, we intentionally design those coefficients to sum to 1 by having ut and then 1 minus ut. And then the one nice thing about this combination is that this allows the norm of ht to indefinitely grow as long as ht minus 1 and ht tilde are bounded. And then that is a nice thing about GRU in a sense that even if you feed forward or you run this GRU update as long as you want, it's very unlikely that the norm of the hidden states are going to explode. On the other hand, with the LSTM, the cell state may explode as you do the forward pass. That can actually sometimes become problematic. But of course, that does come with some kind of limitation because this is a constraint that we put. Unlike LSTM, we can really easily count indefinitely, count number of, let's say, some kind of occurrences indefinitely. GRU has a very difficult time doing so. So, okay, so we now all agree that what GRU update computes is this kind of weighted sum of all the previous states. So weighted sum of all hidden states from the previous steps. Now then, let's start asking one question at a time. And then in order to answer those questions, we're going to relax some of the constraints that have been put there because we started from a recurrent neural network. So first question is that can we free these dependent weights? What do we mean by this dependence weight? Let's just go back all the way to the definition of the update gates. Of the GRU. Okay, I should have actually put it there already, but sorry about that. Let's go all the way back. Oops, let's try this. I can do this, and then I can go much more easily. Yes, this is perfect. So if we look here, where the update gate equation is shown, what we see is that this update gate depends on the previous hidden state. And then this previous hidden state depends also on the update gate. So what it means is that Although in the original unrolled version that we are looking at, that is, there we go, that is here, these weights are not really of the independent weights. That is, across time step, so that is I, for I going from 1 to t, all these weights are dependent on each other. They are not independent from each other. And then now the question is, instead of using these dependent weights, can we use independence weight? That is, instead of doing so, we're going to have alpha I, where the alpha I can be computed using only the values that are available at step I. So we don't have to look at alpha I minus 1, alpha I minus 2, or anything like that. So to do so, we're going to introduce a attention or the weighting function. So this is going to be the weighting function. We already looked at weighting function when we talked about the attention mechanism in the neural machine attention-based LSTM neural machine translation. And then this weighting function is just another neural network that's going to take as the input what the new input is at time step t. I'm sorry, yes, time step t, and then what the hidden state at I was. Because we're computing the hidden state at a time step t, we need to look at the input, that is xt, and then trying to look at how good hi tilde, that is I is before t, is in order to compute this new hidden state. So this weighting function is going to take as the input these two things. And then now, the weight at time step I, that is alpha I, does not depend on the alpha I minus 1 or alpha minus 2, at least via these alpha values. Although you notice that there is still the dependencies coming out of these candidate vectors. So that's our second question. Can we free these candidate vectors? So what do we mean by freeing these candidate vectors is, if you remember, let's go back here. Oh, these candidate vectors, ht tilde, depend on ht minus 1, and then ht minus 1 is going to depend on the ht minus 1 tilde and the ht minus 2, and then ht minus 2 is dependent upon the ht minus 2 tilde and ht minus 3. So in fact, these candidate hidden states are dependent on all the previous tildes, h tildes. So what it means is that they are not really as independent as we want. So what we want is that we want to again break the dependence. And how we are going to do it is to introduce this input function or the input neural net that's going to take as the input at time step I, that is xi, and then trying to map it into the hi tilde without looking at previous hi tildes where I is smaller than I. So this is how we're going to break the dependence of the candidate vectors on the previous candidate vectors. So at this point of step 2, when we have ht equals the weighted sum, so weighted sum of the f of xi, we now finally have completely removed any temporal dependency across these time steps before t. What it means is that we can compute all these terms inside in parallel, largely in parallel, because of the softmax that we are going to use. We cannot really do it perfectly parallel, but largely in parallel, and then simply reduce them by summing them to get the hidden state at time step t. Now, okay, this is fine. So this is how we can get to the attention. But then we realize that there are different ways in which we can use this f of xi, that is the input. Input is sometimes used as to query which of the previous hidden states are important for time step t. And then this query is compared against, in this case, against a key. So it's almost like building a hash table, and each row in this table is the content or the previous hidden states or the previous inputs, And then we are looking for the input that is most relevant to the new input xt. So we need to have the key, and then once the relevant ones are retrieved, that is relevant ones gets a very high alpha I, the key value, we are retrieving the actual value associated with it. So this xi this time works as if it is a value associated with it. So at this point of time in step 2, what we have is that this vector of the input, so the hidden representation or the vector representation of xi serves as both query, key, and also the value. So now the third question is, can we separate out these roles very cleanly? That is, can we come up with a 3 neural network? So we have 3 neural networks. So these are all separate neural networks that takes as input, oops, I'm missing F here actually. Takes as input one of the inputs, so either xi or xt, and then get the representation of x, and trying to get the value vector, so that's going to be v, get the key vector, that's going to be k, and also get the query vector, that's going to be q. And then once I get all those representations, I can compute these weights, or sometimes we call it attention weights, by comparing the query vector of the xt, that is the current input, against all the key vectors of the previous input. There is a k of f of xi, and then we can compute these attention weights. Once the attention weights are computed, we can now compute the weighted sum of the value vectors of all the previous inputs, and that is indicated by V. And then we end up with a hidden state at time step t. Now this is almost like trying to make this attention mechanism or the neural net to mimic what the content or the address-based hashing is. So it's essentially building a hash function into a neural network. So okay, so far so good. But then at this point, you start wonder, do we actually need only one attention? Maybe I can have multiple possible queries, keys, and values. And then that's where we start introducing so-called multiple attention heads. That is, we're going to introduce capital K many attention mechanisms that are going to work all in parallel. So we're going to have the K many query networks, K many key networks, K many value networks. Okay, using K was not great because I used the K for key, but you know, you get the idea here, right? And then for each of these attention mechanism that consists of the query, key, and value networks, we get one hidden state, that is HTK. And then after that, what we end up with is simply the concatenation of all these hidden states from the K many attention heads. And then that's going to be what we get. Now this allows us to have a multiple attention heads that are specialized for different things. For instance, if I wanted to compute a new hidden state, maybe I need to look at 2 different patterns from the previous hidden state. With one attention mechanism, it's much more complicated to capture those 2 different things. But with the multiple heads, all we need to do is make one head to attend to one thing, and then the other head to attend to the other thing. So if you have many heads of the attention, we have a much higher level of flexibility in selecting various aspects of the previous hidden state. Okay, so we have this. Now, up to this point, this is still causal attention in a sense that we are only going to look at the previous hidden state and then run the attention over the previous hidden state. So before we go into the non-causal attention or the extend this into the non-causal attention, let's try to answer one question from Ariel. So for the step 0, the second product in HT is going from K equals 1 to K equals I, or should it be that? Do you, Yes, so the k here goes from 1 to I minus 1, and then j here goes from I to t minus I plus 1. Let me see. Yeah, I think that's correct. And then the second question from Solomon, what do f of xt mean exactly? Xt, yes, xt is the current input. F, the function f here, is the function that's going to process the input. If the input was one-hot vector, just like in the source sentence or the target sentence, then f is going to be a lookup table or the embedding layer. If xi is just a hidden state from the lower layer, then f could just be either identity function or some kind of multi-layer perceptron. So it could be any kind of neural net that is useful for the type of the input you get. Now, we have the causal attention in a sense that in order to compute the hidden state at time step t, we only attend to all those previous hidden state, but then we can extend this into a non-causal attention, as in we let this attention look at the entire sequence. So when we try to compute the hidden state at time step t, for each of the attention head, we're going to look at the entire sequence. That is both all the previous hidden state, current hidden state, as well as all the future hidden state. And then this is possible because we broke all those dependencies in the steps 1 and 2. All these, let's say, candidate vectors and the weights are independent of the other candidate vectors and weights from other time steps. So we can now do it over the entire input sequence. And then everything else stays same, just that we look at everything. Now, when we do this, there is one major issue, is that we can just permute the order of the hidden state and then nothing changes. Before, in this causal attention, although we removed all these dependencies, because we are computing the hidden state based only on the previous hidden states, and we do it one step at a time, what happens is it still does have some notion of the order of the weights, order of the input. And then with the recurrent neural network, it was very natural because the recurrence or the recurrent computation, in fact, goes one step at a time. So it does take into account the order. But with the non-causal attention, there is no notion of positions or the order of the input, because we're going to look at everything equally likely. So instead, what we need to do is we need to very explicitly give the sense of position to the attention mechanism. And how we do so is by adding in so-called positional embedding or position input. And then this P of I is just an embedding matrix or the embedding layer that gives us a vector, one vector per position I. So this position embedding does not depend on the actual input, but only on the position, so that this attention mechanism, the whole attention mechanism, will know which position each of the vector is, which is located. And then that actually tells us, that gives the sense of the position to the attention mechanism. Now, in order to understand about this positional embedding just once more, let's look at this case. When we have this non-causal attention, so up to this step 1, what we realize is that the output of ABCD to this attention is going to be identical to DABC, because everything is computed all together, right? And then they are all independent from each other. So this position specific vectors, or the positional embedding that is being added here, that is a P of I's, they are going to give the sense of positions to this attention. So this positional embedding is going to be added so that it's going to, the attention mechanism is know that the A is in the first position, B is in the second, C is in the third, and then D is in the fourth position. Now that's going to change if we shuffle the order of the items in the input, because in the second case now, D is going to be indicated to be in the first position, A second, B third, and C fourth. So the output of the ATT, ABCD, ATT, DABC are going to be different now. And then there are a number of different ways to design these positional embeddings. One is to simply learn these positional embeddings, as was explored by the Saina Sukdavar et al. From NYU in 2016. Or you can use the positional embeddings based on the sinusoidal functions as proposed or as put forward by the Vaswani et al. In 2017 to make the transformers. And then we are going to look at the more specifics of the positional embeddings later today in the second lab session, as well as how this ATT, how this ATT function is implemented in transformer as well. So one issue with the attention that we have derived so far is that it's inherently linear. Why is it inherently linear? Because it is a weighted sum of the value vectors, and then weighted sum implies that it's just a linear sum of the input vectors. So whatever the hidden state we get is always going to be some linear combination of the input vectors, and then it's really difficult for this attention to manipulate these attention weights to find a very complicated combination. It's just inherently linear. So what we want is to have a post-attention nonlinear layer that's going to allow our network to figure out how to transform these hidden states in a very non-trivial way. And then at the end of the day, the whole power, the entire power of this deep neural network comes from the fact that we have many complicated nonlinear layers that are composed on top of each other. And then what we want is we want this attention mechanism also to be able to provide a highly nonlinear computation. And then that's why we're going to introduce a nonlinear layer right after computing all this attention. That is, once we get all these attention output vectors from the different attention heads, we're going to apply this G that is a nonlinear layer. And then this nonlinear function is often computed or the implement is a multi-layer perceptron or a feed-forward neural network with its own parameters. So we train everything end to end, but then we add this nonlinear function G after applying this attention. Then finally, we get a nonlinear, non-causal attention with the positional embedding that is used by the transformers and any of the state-of-the-art machine translation systems or any state-of-the-art sequence-to-sequence learning models of the recent months or the recent years. So in one slide, this is a full self-attention layer. It starts with the inputs xi to x capital T. So we start with the input. And then for each input, we're going to add the positional embedding in order to give the sense of where those inputs appear. And then we're going to extract for each attention head query, key, and value vectors. And given the query and key values, vectors, we use the attention function to compute the attention weights for that specific attention head. And then given this attention weights, we compute the weighted sum of the value vectors of the input augmented with the position. And then that gives us a vector or the context, the new hidden state at time step T for that specific attention head. So we get a new hidden state at time step T for that attention head K. And then we concatenate all those vectors we get from the K-many attention head and then feed them through this nonlinear function G in order to get HT. Now, of course, this G can be as complicated possible. In practice, this G is going to be applied to each of the hidden state from these multiple attention heads separately, and then they are combined into form a single HT. More specifics are going to be described in the second lab today when we talk about how to implement the transformers and also how to use them. So this is the overall figure of what transformers do. So we talked about the multi-headed attention, how we derive the multi-headed attention starting from the gated recurrent units. And then we talked about the importance of the residual connection that is used here and here and here. Whenever there is some kind of complicated nonlinear function there, we add the residual connection to avoid the vanishing gradient. We have the feed-forward layer that is effectively the G function that makes this attention nonlinear. And then we have the pointwise nonlinearity, which is a part of this feed-forward layer. And then another residual connection for this feed-forward layer. And then finally, we add the layer normalization, which is known to help facilitating backpropagation. So we add all of these together, and then we end up with a transformer. And then of course, we have the positional encodings on both sides. And then we make the encoder that is on this side, that's the encoder, and decoder. So both of them, both encoders and decoders are going to be created using transformers or the self-attention layers alone. And then that's how you end up with attention is all you need paper. We'll go through that. And then this model is really nice compared to the recurrent neural net-based version because we have removed all those direct dependencies when we compute the weights of the attention and also to compute the candidate state, meaning that almost everything can be computed in parallel, makes it much more efficient computationally when used with a GPU, which is specialized for the parallel computation. That's why this kind of transformers have become de facto standard. However, this transformer has some weakness when it comes to inference, which we will be able to learn about it a bit further tomorrow in the first lecture and in the first lab session tomorrow. So today, we have covered 3 important topics. First one is a recurrent language model. And then when we talked about the recurrent language model, we focused more on the internals of the recurrent language neural network. And then in particular, we looked at what are the difficulties of training this recurrent network with the naive transition. And then by identifying the major difficulty as a vanishing gradient, we were able to derive a gated recurrent unit that introduces all those adaptive shortcut connections to avoid the vanishing gradient. And we learned also that those adaptive shortcut connections from the gated recurrent units and long short-term memory units are the motivations behind the residual connection or the residual networks. And then we talked about how we can use this recurrent language model or extend the recurrent language model to build a machine translation system by introducing the encoder that is just reading the source sentence and then using the language model as a decoder in the manner of the conditional language model. And when doing so, we briefly talked about why the attention is important because we do not want to compress the entire source sentence into a single vector. And then after the Q&A with Yashua, we came back to our course and then learned about how we can go from the gated recurrent unit into the fully attentional model that is a transformer by breaking all those temporal dependencies across time. And then that allowed us to make a much more efficient parallelizable layers that we can stack on each other to build a very deep state-of-the-art machine translation and language models, machine translation models and language models. And then that was the wrap up of the attention mechanism. So today, in the rest of the day, we're going to have 2 more lab sessions. Let me just double check that's true. 2 more lab sessions. So you're going to be back after half an hour of break. In the first lab session, we're going to learn about how to build the attention-based LSTM encoder decoder machine translation system. That is the one that we learned in the second part of our first lab session. And then after the dinner break, that is an hour, you will come back if you're in Kigali at 7 p.m., if you're in Accra at 5 p.m. to learn about how to build a transformers for machine translation and how to use a FAIRSIG, which is the open source library released and maintained by the Facebook AI research to build a state-of-the-art machine translation system without worrying too much about how to implement all these things yourself. Then that's it for this lab session. Please do enjoy your break, half an hour. Please be back by 5 p.m. for Kigali and then 3 p.m. for Accra. I'll talk to you later then. Bye-bye.
Thank you.